Okay, so in this question, we are given a 4-meter diameter water tank that consists of two half cylinders, each weighing 4.5 kilonewtons per meter. So each meter length of each half of the cylinder weighs 4.5 kilonewtons. So basically, if this whole thing was 1 meter long, then the top half would weigh 4.5 kilonewtons and the bottom half would also weigh 4.5 kilonewtons. Yeah, cool. We're told that it's bolted together as shown in the figure, so these are the bolt holes over here, so it's bolted there. Yeah, and then the support of the end caps can be neglected, and we're asked to determine the force induced in each bolt. Okay, so we can draw our free body diagram, but before we do so, let's try and visualize what the pressure in the whole tank would look like. So at the top over here, you'd have pretty modest amounts of pressure, but then as you start to decrease in height, your pressure would get larger and larger. Okay, and then as you round the thing, it gets smaller again. Okay, so as you increase your height, then your pressure gets larger, and you can see that well, you might not be able to see it, but at every single horizontal point, so if I were to draw a line here, right, the pressure along this line is constant, right? So its direction might change, but its magnitude won't, if that kind of makes sense. So the pressure at this point over here and the pressure at this point over here would be exactly the same in the horizontal direction, but because pressure acts normally to the surface, they would have, if you were to like sum the forces caused by that pressure, you would have a net vertical force. So if I were to draw that portion, so this is just a curved portion of the tank, so you have like the rest of it kind of like that, right? So this is just a curved portion, and then remember, pressure always acts normal to the surface. Okay, so you have that as your pressure, and it's the same in magnitude because you are at the same horizontal distance. Okay, so if I were to take the if I were to split it into components, I would get a horizontal component and a vertical component, and then again over here, horizontal component and a vertical component. So you can immediately see these two horizontal components will cancel out, but these two vertical components will act together to kind of push this whole container upward, right? So yeah, in these kind of questions, we're not necessarily concerned with the horizontal forces because they're going to cancel out anyways. The thing we're concerned about is the vertical forces. Also because the vertical forces are different as you go down. So over here, they're very, very small, not zero. And then at the bottom, they're very high. So that's the thing that's actually putting stress on your container or whatever you're dealing with. Okay, I hope that makes sense. So when dealing with these kind of questions, you want to first look at a section of fluid, and then from there you kind of transfer the resulting force onto the body you're working with. Okay, so to represent that, let's say that the water that's inside the tank, we're going to take a slice of it, right? So I can draw this in 3D, and hopefully it will make things easier to see. I'm basically taking a small slice of the fluid, so the pink outline is the tank, right? And then the blue is the slice of fluid that I'm taking, right? So it kind of looks like that. Okay, and then I'm going to analyze it from this view over here. Okay, so the fluid has its own weight, okay, and then it's also going to have forces from the surrounding fluid. Okay, so remember, there's still fluid all around, so there's fluid in this area here, but we're only analyzing a small section of it. So you can imagine if we treated this as like a block, right? So we're pretending this is not a fluid anymore, pretending that it's like a block or whatever, and then you have water sitting all around it. The water is going to press up against the block, right? It's going to press up against the block. So there's going to be a force over here. We're going to call that FH, from the fluid kind of pushing it to the side. Okay. And then we're also going to have a reaction force. Okay. So it might be kind of difficult to see the reaction force, but let's say we didn't draw that reaction force. We're going to have the weight of the fluid, okay, and then we're also going to have a resultant force, okay, so we're going to call this FR, and then we're going to call this W for the weight. So the resultant force is basically from the pressure, right? So this in this diagram over here, you can see that you have all your pressure thingies acting outward, all your pressure vectors, I guess, they were acting outward, and that's the pressure acting on the vessel, right? So the fluid is pressing on the vessel, right? And the vessel will be pressing on the fluid as well to kind of counteract that force. So Newton's law, basically. So yeah, the force from the vessel pushing back onto the fluid, that's what this FR is. Okay. It's basically the resultant force from the pressure of the fluid. Okay. So if you were to like take a vector sum of these vectors here, this arc, you'd get like a resultant that points that way. But then now we want the equal and opposite vector of that, and it's going to point that way. Okay. I hope that makes sense. Okay, so if we look at this diagram over here, we have a force that's pointing in that direction. Cool. And you can see it has a component that will act downwards and a component that will act this way. And then the weight is acting downwards. Okay, so if we were to do sum of forces in X equal to 0, we're sorted. If we were to do sum of forces in Y equal to 0, we're not sorted. We have an issue. Okay, so let's assume that maybe we drew this vector in the wrong way. Is it possible that this vector FR could be facing in the other direction? Short answer, no, because the fluid itself is pushing against the vessel, like it is here. Okay, and since it's pushing against the vessel, it's gonna have a resultant force going that way. And then remember, FR is the vessel pushing back on the fluid. Okay, so it is indeed in the correct direction. So we need a resultant force over here at the bottom to counteract this, to prevent it from accelerating downwards. So you can see that the fluid at the bottom, right? So you kind of have this situation. So let's say that's the center of mass. You have the weight, you have that thingy, and you have that. And then this fluid at the bottom, you're kind of wanting to compress it. So the container is pushing this fluid. It's pushing the fluid this way, right? And the weight of the fluid is pulling it downwards. So the fluid in this section experiences a compressive force, and it's like, I don't like that. So it rebels, I guess, and is like, yeah, I don't know. It pushes back basically with a reaction force R. Okay, cool. So now with this free body diagram, we satisfy equilibrium in the Y direction. So we are happy. Cool stuff. Then we can do, so sum of forces in X won't really catch you anyway. So sum of forces in X will just tell you that FR in the X direction is equal to FH, right? And cool, that's fine. But also remember, all your X forces cancel out. So remember this example. Your X components will cancel out. It's the Y components that we're concerned with. So we're not going to do sum of forces in X. We're going to do sum of forces in Y. So sum of forces in Y equal to 0 will give you minus FR in the Y direction plus R minus W is equal to 0. Cool. So we can find W, right? So W is the weight of this section of fluid. So it's not just the 2D section of fluid, it's the 3D section of fluid, if that makes sense. So it's this whole blue region over here, this whole blue region. So we're going to calculate the weights of that. That's pretty easy to do. And then FRY, we don't really have an expression for that. So in order to find FRY, we need to find this reaction force R. Okay, so we can do that by saying R is equal to the pressure at the bottom. So I'm going to call this point over here, I'm going to call that point A. So R is just equal to the pressure at point A times the area right? And the area that you're looking at is this bottom area over here, right? So this area there, okay? So that's kind of, yeah, that's basically the area you're looking at. So the pressure is acting at point A, and then to convert that to a force, you multiply it by this blue area over here. Hope that kind of makes sense. Yeah, so in order to get the pressure at A, we're just going to use rho GH, okay? But we need to be careful. So we also have a vertical column, right? And we were told that this has a height of 2, right? So we need to bear that in mind when calculating our pressure. So we can say that PA is equal to rho of water, because we're dealing with water. So rho of water times G times H, where H is going to be equal to 4, not 2. So it's going to be the total height. So the height to the very top, basically. And then that times the area. Which will, do I have the answer? Which will be equal to, sorry, that's not, the pressure is not times the area, the pressure is just that, and then R will be equal to rho of the water times G times H times the area, which will be rho of water is 998 times 9.81, and then H, instead of it being 2, I'm going to say it's 4. So it's the distance from the top over here to this point over here. So this distance is 2, that distance is also 2. So 2 plus 2, 4. Cool stuff. And then times the area. And the area is gonna be 2. So you have that, this is 2, and then this length over here, this length L, we can determine it from the bolt spacing. So they tell us that the space between bolts is 25 centimeters, so that's 25 centimeters. So 25, 25, again 25, again 25. So this is basically 100 centimeters, which is 1 meter. Okay, so the length of this entire thing is 1 meter. So we're going to say it's 1 meter multiplied by 2. That's our area. And then that will give you a value of 78,323.04 newtons. Okay. And then from there we have R. So let's find W. So W is simply equal to the density of the water times the volume of the water times gravitational acceleration, right? So density times volume gives you mass, and then mass times G gives you weight. Okay, so this will, if you plug in the numbers, this will be 998 times the volume. So the volume is the volume of this specific column. So this portion, this blue portion over here, it's not the volume of the entire cylinder, because remember, you're only analyzing this small section. So yeah, just keep that in mind. So it's going to be a quarter of the volume of a cylinder. So 1/4 times the volume of a cylinder. Volume of a cylinder is pi times r squared, so pi 2 squared times the length, which is 1 meter. Okay, and then times 9.81. And then you'll get that your weight is equal to 30,757.38588 newtons. Cool. So that's your weight. And then knowing these values, you can find, knowing your weight and knowing R, you can find FRY, fry. Cool. Then you'll get FRY equal to 47565.65412 newtons. Cool. It's all good and dandy. We found the reaction force in the y direction, but that doesn't really tell us anything about the bolts. So we've analyzed the column of fluid now. So next thing we do is we transfer any forces that we can to the actual body or the casing, right? And we're going to draw it again, and we're going to draw the same portion. Okay, so we calculated for this little portion, so we're going to calculate for that same shape basically, but now we're dealing with the outside tank. So this is the portion that we're analyzing. Okay, cool. So over here we're going to have FB, right, the force of the bolt, and then we're going to have the weight of the tank, and then we're going to have FR. Okay, so the fluid is now pushing up against the vessel. Okay, so the fluid, you can think of it as having like pretty high pressure, and it's like pushing on the vessel. Yeah, cool. So that's our free body diagram. Again, we're not concerned about forces in X. You would think that it's unbalanced, blah blah blah. If you draw the rest of the tank, you'll see that there's another force, the side, that balances it in X, but you'll also see that in the Y direction you would have a resultant force. So yeah, again, we're concerned with only the Y direction. So if we were to do sum of forces in Y equal to 0, we'd get that FRY, our fry, minus FB minus W of the tank is equal to 0. And then we know what fry is. We can find the weight of the tank, so basically know what that is, and then this is what we're looking for. So cool, let's find the weight of the tank. So the weight of the tank, we're told that the tank consists of 2 half cylinders, and each half cylinder weighs 4.5 kilonewtons per meter. So the length of this is 1 meter long. So the top half will weigh 4.5 kilonewtons, because the length is 1 meter. If it was 2 meters, then it would weigh, 9 kilonewtons, 4.5 times 2. Yeah. Hope that makes sense. But remember, we're dealing with this portion, so we're not dealing with the entire length of it. Okay, so this is the portion we're dealing with. So we need the weight of only this portion, and we know that the weight of this entire portion, so if we draw it as like a full half of the thingy, this weight would be 4.5 kilonewtons. So we just need to half that to get this portion here. Yeah, hope that makes sense. So we're gonna say 4,500 divided by 2. That's the weight of the tank, or at least the portion that we're dealing with. Cool. And then we can rewrite our equation for the bolt. So force of the bolt will be equal to, this is wrong, so it's 4,500. Oh no, it's correct, sorry, I thought this was kgs. It's in newtons, which is fine. Okay, so we can rewrite this equation over here. So the force of the bolt will be equal to Fry minus W of the tank. Cool. And then the force of the bolt you will get to be 45,315.65412 newtons. And if you check the memo, then you'll realize that's not the correct answer. And the reason why is because we've basically calculated a resultant force for each and every single bolt. So we need to divide this force over here by 5. So if you say FB divided by 5, then you'll get 9063.13 newtons, which is the correct answer. Okay, I hope that makes sense.